In this screencast, we're going to talk about the chemistry of the amines. So what you'll notice is that these are straight from my lecture notes. And so basically what I'm going to do is just go over them and use the laser pointer to talk about the specific points. So the general features of amines. Amines have the amino group. So R can be anything. The amino group is NH2. So that's indicative of an amine functional group. So amines are classified by the number of carbons that are bonded to the nitrogen. So primary amines, such as ammonia, so you have nitrogen plus 3 hydrogens. So methylamine, you're substituting one of the hydrogens for a methyl group. So the IUPAC name would be methanamine. So we're dropping the E from methane and we're adding amine, so methanamine. So ethylamine, ethanamine. We can also have a cyclic substituent, so cyclohexylamine or cyclohexanamine. So these are all primary amines. So basically they have one carbon substituent bonded to them. Secondary amines have 2 carbon substituents, for example, diisopropylamine. So you have your isopropyl groups, and then you have a single NH bond. So tertiary amines, you have now a nitrogen with no hydrogens and 3 carbon groups. So this is triethylamine. And here we have ethyl diisopropylamine, so ethyl diisopropylamine. So we can also have the nitrogen inside a ring. So these are called heterocycles. So the 5-membered ring here is called pyrrolidine. The 6-membered ring is called piperidine. We can also have aromatic amines. So the amine bonded to a benzene ring, that's called aniline. When the nitrogen is inside the ring, that's called pyridine. So if we have a 5-membered ring, this is called pyrrole. And then we have another 5-membered ring with 2 nitrogens called imidazole. Now, if we look at these 3 heterocycles specifically, and we sort of take this one as the one in common between these two, this nitrogen here is the same as a pyridine nitrogen. And this nitrogen here is the same as a pyrrole nitrogen. And so the difference between those 2 nitrogens is that we know that nitrogen has 3 substituents in a single lone pair. So let's look at pyridine. We count 1, 2, 3 substituents, and then the lone pair here resides in an sp2 hybrid orbital, and that's the same as this nitrogen and imidazole. Now, if we look at pyrrole, we have 1, 2, 3 substituents. So the lone pair is actually in a p orbital. So these are the same. And so the difference between these nitrogens now, so pyrrole versus pyridine, and what you see in imidazole that has both, this nitrogen is actually more basic. And remember, what we mean by basic is the ability to abstract a proton, because the lone pair resides in an sp2 hybrid orbital. Here it does not. It resides in a p orbital that's in conjugation with these other pi bonds. So amine structures, acyclic and these cyclic amines tend to have a sp3 hybridized nitrogen. Here's your lone pair, here's your 1, 2, 3 substituents. If these are 3 different substituents, you can actually have inversion about the lone pair. So imagine like an umbrella inverting. So the lone pair is on the right, there's an inversion, now it's on the left, and the energy barrier is about 25 kcals per mole. And so these molecules are actually enantiomers. But this inversion happens so fast at room temperature that you really can't isolate the enantiomers. Only when these groups get really bulky can you then sort of freeze out one enantiomer. So properties of amines. Amines can undergo hydrogen bonding. So we've seen that as well with alcohols. Again, hydrogen bonding is a non-covalent interaction. So for example, if we have methylamine, we're showing 2 molecules of that, and then we're showing the hydrogen bond here is this dotted red line. That's typically about 21 kilojoules per mole. And hydrogen bonding alters the physical properties of the bulk material. So because you have this hydrogen bond donor, so this hydrogen in this molecule is being the donor, this lone pair is being the acceptor, and now here vice versa. There's this attraction, and that attraction tends to increase the melting points, increase the boiling points. So notice for tertiary amines, they can be an acceptor only because there's no hydrogen on the nitrogen. So if we consider ethyl diisopropylamine, that's going to be miscible in water because water can donate a hydrogen bond. The amine can accept it. So you have this interaction, and so that would make this miscible in water to some extent. So our second key concept is understanding the basicity of amines. So again, basicity is the ability to abstract a proton. So this is normalized on a pKa scale. So let's consider what this really means, because pKa is acidity, pKb is basicity, but when we're talking about basicity, all the experiments are measured on the acidity scale, so there's a relationship that we have to discuss here. So let's consider an aminium ion, so a aminium ion, that's a protonated nitrogen. So in the presence of water, and we're going to do an acid-base reaction. So here's your acid, water's the base, it's abstracting this proton, we get the amine, and then the hydronium ion. So the equilibrium expression, you'll recall Ka is the product. So the product of these molar concentrations, that's what the square brackets mean. So this concentration of the amine times the concentration of the hydronium divided by the concentration of the aminium ion. And remember that water gets folded into this Ka, so that's why you don't see it here. So the pKa, again, a p function in chemistry is the negative log. So if we take the p of both sides, pKa, we get the negative log of the Ka. And so the stronger the pKa of the aminium ion, the weaker the amine base. So again, this is an inverted scale because we're measuring the pKa value. So if we have ammonia that's been protonated, that has a pK of 9.26. If we have methylamine versus ethylamine, notice that the pKa, the acidity is increasing towards the ammonia. So because it's increasing this way, where there's less carbon substitution, the basicity has to have the opposite trend. So we can then infer that a tertiary base is stronger than a secondary, stronger than a primary, and stronger than ammonia. So the stronger the pKa of the aminium ion, so the lower that number, the weaker the amine base, again, because they're inverted. So what about aniline? So again, benzene ring attached to a nitrogen. So this is called aniline. The pKa of the anilinium ion, when this is protonated, is 4.58. So because this is getting to a low pKa, that means this molecule as shown is a weak base. And so why is it a weak base? Remember, basicity is defined as the ability of the lone pair to abstract the hydrogen, the proton. This nitrogen lone pair is not really available to abstract a hydrogen because it is delocalized into the ring as shown through this resonance here. So this lone pair gets delocalized. Actually, we should have plus charge there. So now we have plus, minus, neutral. We started neutral, we're neutralizing the charge here. We can then move this charge around to this position. You see it here. And then we can move it back here. So the nitrogen lone pair is delocalized into the benzene ring via resonance. The nitrogen is therefore less basic. So what about nitrogen when it's in the ring? So now it's sp2 hybridized. This is pyridine. Pyridine is a very good base. It's going to abstract a hydrogen from hydrogen chloride. We form pyridinium chloride. This molecule has a pK of 5.23. So again, what you need to understand is the difference in basicity of these nitrogens. This pyridine nitrogen is more basic than this aniline nitrogen. So pyrrole, this nitrogen, again, the lone pair is in a p orbital. If we treat with HCl, the pyrrolinium ion now has a pK of 0.4, so this is pretty acidic, right? So the pKb of this is going to be very high. That's a weak base. We have a strong acid. This is therefore a weak base. So we're going to finish up this screencast looking at the reactivity of the amino group. So again, features of the amino group. Let's just consider any carbon substituent. You have a nitrogen, a lone pair, which is a nucleophile. This NH bond has a pK of about 35. So this is a very weak acid, this NH bond. So amines typically don't function as acids because that pK is very high. It's a weak acid. So they act as either bases or nucleophiles. And again, a base, its action is to abstract a proton. A nucleophile, its action is to form a bond to something other than hydrogen. So amines typically undergo alkylation or acylation. So let's look at some reactions here of amines. So these are SN2 reactions, the Hell-Vollard-Zelinsky reaction, and then amination. So if we take a carboxylic acid and we treat it with bromine in the presence of elemental phosphorus, and then do an acidic or an aqueous workup, we're going to get alpha bromination. So remember, here's the alpha carbon. We have two hydrogens. One of them is substituted for bromine. So we have this alpha bromo acid. We have a good leaving group. Let's treat that with ammonia NH3 and an excess. The first equivalent is going to do an acid-base reaction. So we're going to get a deprotonation there, and that's what we see here. We've now formed this ammonium salt. The second equivalent is now going to displace the bromine here at the alpha position. And so this is an alpha amino acid in the salt form, and we'll talk about these in this module as well. So another way to introduce nitrogen into a molecule is through azide displacement and then reduction. So here we have a primary bromide. We know that bromine's a good leaving group. We have sodium azide and DMSO, dimethyl sulfoxide, so polar aprotic solvent. Azide is the nucleophile. It displaces the bromine. We get the azide. So you should practice drawing out what N3 is, Lewis dot structure, so you know what that looks like. Then we can reduce that with either lithium aluminum hydride or hydrogen gas with palladium on carbon. And so essentially what that's going to do is form the primary amine by reducing off N2. So we have NH2. So this is a primary amine. If we have this same starting material now, in this case, we can do cyanide displacement and then reduction. So again, SN2 reaction with potassium cyanide, displace the bromine. DMF is dimethylformamide, a polar aprotic solvent. So now look what we've done here. We have another carbon. We're at oxidation state 1, 2, 3. We're then going to reduce that with hydrogen gas and rainy nickel or lithium aluminum hydride. So again, this gets reduced now to the CH2. The nitrogen also gets reduced. These molecules are called homologs because notice there's a CH2 spacer. So this is a homolog of this compound. This basically means we've added an extra CH2 group, primary amine as well. And so the last one is the Gabriel amine synthesis. So notice in all of these reactions, we're starting with the same alkyl bromide. We're using this molecule here as the source of nitrogen, potassium thalamide. So this is basically a nitrogen anion that attacks this carbon, bromine leaves. You get the byproduct of potassium bromide. So this nitrogen here is now, we call this a protecting group. So the nitrogen protected, we can deprotect it using hydrazine. This is also rocket fuel. So hydrazine is basically two equivalents of ammonia that have been bonded. The nitrogens are bonded together and we remove a molecule of H2. So we have NH2, NH2. So what happens here is that this group gets deprotected. We free up the primary amine. So this product is actually the same as this one when we use sodium azide. And then this part of the molecule is removed as that heterocycle. Alternatively, you could use acidic conditions to deprotect that and you get the diacid. And so in the last slide here for this screencast, amines can also undergo acylation. So we have a primary amine, we have an acid chloride, so acetic chloride. And if we remember from the last module, this reaction, this is a nucleophile, this is an electrophile. We're forming amine plus an acid chloride. This gives an amide. And again, the mechanism of this is nucleophilic acyl substitution. So the chlorine gets substituted for the nitrogen. Now this is a secondary amide. We count 1, 2 bonds to that nitrogen. We can reduce that amide now with lithium aluminum hydride. So we have 2 carbons. This carbon's at oxidation state 3. It's now at oxidation state 1, and we end up with a secondary amine. So this process now, starting with a primary amine, doing an acylation, we get a secondary amide. We reduce it, we get a secondary amine. So down in red here is just some example problems on my notes from another book. So in this problem here, basically we're taking a primary amine in the presence of a ketone, an acid. So we have primary amine, ketone, that's going to form an imine. We can then subsequently reduce that imine with sodium cyanoborohydride, and this is an example of reductive amination. So we count 1, 2, 3, 4, 5. The imine forms there, it then gets reduced. Now we have a cyclic amine. So the primary amine, this is now a secondary amine. So if we imagine another reaction, amide dehydration, so we can make this molecule by treating ammonia with benzoyl chloride. We can then dehydrate this primary amide in the presence of phosphorus oxychloride. And essentially what this does is form a nitrile. So the way that this mechanism happens is that this amide, this is a primary amide. We can show a resonance form. There's a resonance arrow. The nitrogen lone pair is delocalized onto oxygen. So we see that here. We see the balance of charge. We see the nucleophilic oxygen attack the phosphorus. So this is sort of like acyl substitution that's happening here. So the phosphorus then eliminates out a chlorine. This oxygen is now activated here. This chloride can then come and abstract this hydrogen, so we lose HCl. This nitrogen lone pair then can do an elimination to remove that. That's a good leaving group. So it leaves. It displaces a chlorine. That then abstracts this hydrogen from this nitrilium ion. We lose HCl, and that's how we get this nitrile. So in this screencast, we've looked at a couple different ways to incorporate nitrogen into a molecule to make different amines, of which we learned the different classifications, primary, secondary, and tertiary, due to the fact that amines can act as hydrogen bond donors and acceptors, changes their physical properties, and can make them miscible with water.